Now? Oh, okay. What's up, people? So this week I heard that many of you have a lab quiz and a chem exam. So when I took the lab quiz last semester, and when they told me that it was mostly, they told me it's everything you learn in chem lab. Nah, that was bullshit. When I took the quiz, it was only molecular modeling. So this packet right here, people, that's your quiz right here. At least for me when I had it. So my recommendation is study the shit out of this. And you know how every lab you have a PowerPoint before a lab? The PowerPoint before the molecular modeling lab, that's basically your study guide. So the notes I have today is basically a repetition of that PowerPoint. So look it up. So I'm just gonna go do like a little recap and some example of the concept of molecular modeling. So the first thing we're gonna talk about is electronegativity. And it's just simple as it is. Looking at this periodic table, this location here on the upper right portion of the periodic table is where the elements are have the most electronegativity. So right here, this is helium. Helium has the most electronegativity out of any elements. So if we're going to compare two different elements such as fluorine or selenium, fluorine is closer to this point right here, meaning that's more electronegativity. So you have to know this in order to find the dipoles and determine whether something is polar or not polar. So just remember that the closer that element's right up to this corner, the more electronegative it is. So moving on, these next four concepts, they're all math. They were in my quiz when I took it. So know these concepts. The first concept is val, or valence electron, and basically what it is the sum of the valence electron of each element. So basically, if you had BeCl2, you define the valence electron of Be, and you have to add it with the valence electron of Cl times 2, because this is BeCl2. We'll go more example of that. Just remember, it's the sum. Sigma means sum of the valence electron of each element. So we'll get more example of that. The next concept is stab, or stable noble gas configuration, which is NGF, noble gas configuration. It's just like valence electron, except it's the sum of the electrons in the NGC for each element. And basically every single element in the periodic table have 8 electrons except 4, and these includes helium. We have 2 electrons. What's B?
Beryllium.
Beryllium has 4 electrons, and barium and aluminum both have 6 electrons. Boron?
Or is it BA and then AL, or BA?
You guys just check the periodic
Capital
table.
B just by itself is boron.
Boron. So basically, the way I memorize these 4 is the term HB ball, pronounced ball. H for 2, B for 4, and ball, B in aluminum, is 6. Everything else is 8 electrons. So if you don't get so that's just a way to memorize this. So remember to memorize the 4 unique concept. Concept is not a good word. Remember the word HB ball. Just memorize that. And remember, all other elements are 8 electrons. So those are the first 2 math-wise that you have to know for the quiz. The second 2 are bond and lone pairs, and we're basically determining how many bond electrons and lone electrons are in between element when you make the figure. So bond is like here, it says bonding electron pairs of electron found in the space between atoms. And I emphasize space because right down here, this part right here is a bond, is a bonding. You don't include these. These is what we call a lone pairs, but I'm getting ahead of myself. So the formula for bond is stab minus val. So this minus this. Memorize this, because you're gonna need to know it for the quiz. And lone pair is gonna be electron pairs. It's the electron pairs. Is unshared of electron are localized on an atom. So basically, this is electron pair. This is a lone pair. This is a lone pair. This is a lone pair. You get the gist. Mostly bond pairs are going to be a straight line. That's how you should draw it. And lone pairs should stay as dots. And the formula for lone pair is valence minus bond. You have to know these for the quiz, at least when I took it, because I forgot the formula and it screwed me over so badly. So memorize that. And just remember what each looks like. So that's the math, basically, the 4 concepts of math. And so now we're going to go on more conceptual ideas. So the first idea we're going to talk about is naming. In this packet, you have a whole bunch of namings, and we're going to get how to memorize that later. And I'm just going to tell you what they basically means. There's an electron geometry and a molecular geometry, and they're two different. They're like 2 different names for one structure. So every of these molecular formulas have 2 different names, basically. So the electron geometry, to determine the electron geometry, you have to look at the electron pairs. So I reiterate, the electron pairs. The space between an atom. So for right now, this is this formula is going to be BeCl2. How many electron pairs are there? There are 2. 1, 2. And this will help you find out what type of element it is, because you have to look at this chart. I will show you how to memorize this a bit, but that one, BeCl2, has 2 electron pairs, meaning that it's a linear geometry. And another thing to determine is molecular geometry. Basically, molecular geometry is more like the specific, or more of like giving like it more like a specific name to it, because a lot of the formulas, they can have the same electron geometry, but they can have different molecular geometry. So if we look at this, how many lone pairs does this element have? And when you look at lone pairs and electron geometry, you can only look at between the middle element. So right now, Be has no lone pairs. If it's like this, that means it has 2 lone pairs, 1 lone pairs, and 2 lone pairs. But right now it doesn't. So that means that since we look back to this chart, if there's no lone pairs, it stays as linear. So that's kind of like an example. We're going to go more of it. So I'm going to reiterate, to determine electron geometry, only look at the electron pairs. For the molecular geometry, only look at the lone pairs. And you have to look in between the middle of the element, like Be right there. So I hope that makes sense, but we're going to go more examples. And now the next concept we're going to learn is about polarities. And I know in the chart, they talk about poles and dipoles. And I'll tell you that when a compound is polar, it has a dipole. When a compound is non-polar, it does not have dipole. So very simple relationship. And basically there are a few rules to determine if something is polar or non-polar. So we're going to talk about polar first. For polar, the first rule is if the charges travel the same direction, meaning that, like I like to say it, they're going inward or literally one direction. So I'm going to send you an example right now. Yeah. So we're going to look for a different marker. So here's our first example, NO, right? So I'm going to draw NO for you guys, and this is what NO looks like. So if you look at your periodic table, the first thing you want to do is determine which element is more electronegative. And right now, O is more electronegative. So that means all the electrons are going to go this way. Do you see how they're going the same direction? If they're going the same direction like this, meaning that all the electrons from N are going this way, it means it's polar. So that's the first rule. We're going to go to more example on that. But keep that in mind for now. And now the second rule is if polar shares different lengths. And I think we're going to do an example on that later, so I will go back to that. Just remember these 2 rules. But mostly when it turns when something's polar, this is kind of like the main rule. The second term is nonpolar, and like I said, nonpolar means have no dipole, and there are 2 rules. When the charges travel to different directions, see how these 2 differ? polars go to the same direction, while non-polars go to different directions. So let me draw a example right now. No, that's too much work. Oh yeah, here. And this is BF3. If you look at your periodic table, fluorine? Fluorine? Pretend this is fluorine. Fluorine has more electronegativity than B. Yeah, F has more electronegativity than B, meaning that the way I show more electronegativity, as you guys saw, is I draw arrows, meaning that all this electronegativity from B is going to go towards F. So all the electronegativity B will go towards F, And since we're going by the rules, a compound is nonpolar when the charges travel different direction. You see, all the charges go a different direction, and the reason why this is nonpolar is because all the electrons, they're going out different directions, meaning that they're stuck. There's nowhere to go. After they go out, all the electrons, they're just like stuck in a bubble, so they can't make a polarity. So that's kind of the concept. That's the concept behind like the directions. But I'm gonna show you another rule of polars. When something's polar that I forgot to write. So right now, B, F3 don't have any lone pairs, right? So let's just say what happened if it does have lone pairs, because you're gonna get example with lone pairs. So let's look at this. So now there's 2 lone pairs on each side, right? To make this make sense, I want you to imagine that you're in a spaceship, okay? And have you watched those movies where this is the window, right? And this window breaks and everything gets sucked out of the ship. I hope you guys know what I'm saying. Think that way for this type of structure with a lone pair. Because basically when there's a lone pair, all the electronegativity are gonna go out this way too, like a window. And the thing is, since this is like a window, like outside of the shell of the formula, this is going to be a polar example now. Because it's polar because all the electronegativity, they're not stuck into one element anymore, they're going out. So basically to reiterate, if there's no lone pairs in this example, it's non-polar because they're stuck. But since they're lone pairs now, all the electrons go out, meaning they're not stuck anymore. So I hope that makes sense. Do as many examples, you will see the pattern. And going back to nonpolars, the second rule is when you're naming the structure of a formula, if it's linear or planar, it's automatically nonpolar. Because mostly, if you look at the shape of those of linear and planar, all the electrons will get stuck. So basically, are the main rules. I hope that helps. If you have any questions, you can ask. And we're going to do some examples right now. Pause.